Can we hear you, Dr.
Yes,
Kumar?
yes.
Good.
So am I audible?
Yeah, we can hear you. You can start talking. Yes.
All right, all right. Thank you, thank you. So my name is Ankit Kumar. Hello all. So I am a PhD student at IIT Kanpur. The title of my talk is Measurement of Slow Neutron Flux During Heavy Water Electrolysis. My thesis supervisor is Professor K.P. Rajiv, and we have been working on ALIENA for the past 6 to 7 years. In my master's also I did some projects, and then I continued my PhD on the same topic. So let's start with the outline of the presentation. Okay, so you may follow the laser pointer, or which is visible. So first we'll start with the background of neutron detection in electrolysis experiments. And then we'll move on to a quick introduction to CR39. This is solid state nuclear track detector, Columbia resin 39. Then we will move on to how we can use this CR39 to measure slower neutron fluences even in a mixed radiation field. So by mixed radiation field, what do I mean? I mean a field in which there are slow neutrons, there are fast neutrons, and there are charged particle fluences as well. And next, the main part of this PowerPoint, the detection of slow neutrons in electrolysis experiments. So basically, first I will justify how this method is suitable for this measurement in electrolysis experiments. And at last, summary and way forward. So let's start. So let's first have a look at the typical experimental setups which is involved in such kind of experiments. So figure A shows a small beaker which has electrolyte in it. In this case, it is palladium chloride in heavy water. We have a platinum cathode and we have a graphite anode here. So after a suitable voltage bias, we can start the electrolysis. And in order to look for the nuclear emissions from these reactions, we will have to integrate this setup with a suitable nuclear detector. Let's have a look at some of the cases. So this is one of the cases which where I am trying to measure photon being emitted from this electrolytic setup. This whole setup is being placed in a lead cave, and what you see is a sodium iodide detector. So two sodium iodide detectors trying to measure photons. Again, if you want to measure particles being emitted from cathode, we'll have to place particle detectors inside the electrolyte, because it may be the case that the particles may not have enough energy to travel outside, and so we use CR39 detectors in close contact with the cathode, and this itself can be placed inside this cell, and that's how we can measure the charged particles. Figure D shows few more detectors that we use. We have spectrometers, we have GM counters, we have this research level spectrometer, neutron spectrometer, and an experimenter would also like to measure the transmutations isotopic shifts that can emerge on these cathodes. So figure E shows the electron dispersive spectroscopy machine that we use here at IIT Kanpur, and then somebody may be interested in isotopic analysis, so we use ICP-MS, and then we have TOF-SIMS at IIT Bombay. So these are all the typical experimental setups that are being used in electrolysis experiments. So let's move ahead and talk about the neutron detection experiments. A quick summary: we know about the Flashman and Pons experiments, which were published in 1989. They used BF3 detectors, boron trifluoride detectors, to claim neutron emissions. And then we have another Italian team which tried to measure tritium neutron emission in heavy electrolysis with palladium and titanium cathodes. This was published in 1992, and they use liquid scintillation detectors. Moving on to the more modern experiments which are relevant for this PowerPoint are related to the co-deposition experiments. I hope everybody know about these co-deposition experiments. Co-deposition simply means that we are co-depositing palladium as well as deuterons onto the cathode. So, so this team used helium-3 neutron detectors to measure neutrons. So this is their setup. This is the electrolytic cell. This is a helium-3 tube detector, is surrounded by the moderator, and then we have the red one is a gamma detector shielded by LED blocks to reduce the fluctuations. And so in the same co-deposition experiments, triple tracks has also been observed on CR39 as opposed to this helium-3 liquid scintillation BF3, which were all electronic detectors or electronic based detectors, which are typically called as active detectors. CR39 is a passive detector. It does not use any kind of electronics. And so let's have a look at how a triple track looks like. This I have taken from this paper. So you can see a particle which is emanating 3 particles. So it is interpreted as incoming fast neutron is causing a carbon which is already present as a constituent unit of CR39 and causing a ternary fission of that carbon into 3 alpha particles. So these 1, 2, 3, what you see are 3 alpha particles emanating out of a carbon due to a fast neutron failure. So typically these are the experiments that have been done, and my aim so this is active detectors versus passive detectors. So we have to understand that any kind of detector has their own plus points and they have own demerits. So for active neutrons, we can say that the electronic signals could be a demerit, and for the passive detectors, the major demerit is that we cannot see the real-time signals. So it is always going to show us an integrated signal. So my aim is to utilize CR39 to look for thermal neutron signals in electrolysis experiments. So let's move on and understand how CR39 works. So in figure A, you see a transparent sheet popping out of this pouch is a CR39 material. And when you zoom in, this figure B is a zoomed in image. This is a 0.9 by 1.2 mm square image, microscopic image. You see, this is CR39. And this is, and so how is it used to detect nuclear particles? So we are going to demonstrate it using schematic C. So you see that this CR39 is nothing but a thermoset polymer. And when a nuclear particle enters into this polymer, it breaks the chain of the polymers. The condition to generate a permanent damage in this polymer material is that the incoming nuclear particle or the incident nuclear particle should at least deposit 15 kiloelectron volt per unit length. The length is measured in microns. So the condition for permanent track registration or permanent damage in polymer, permanent damage in polymer, is that the incoming neutron should be, incoming charged particle should be able to deposit at least 15 kiloelectron volts per micron in this medium. So once a particle enters, it's going to create this damage in polymer. So the polymer strands are going to be basically going to be broken, but this damage is not visible with naked eyes. So we will have to do some kind of etching. And so the standard etching process of CR39 involves nearly 6 molar sodium hydroxide, and the etching is done for 6 hours at 70 degrees Celsius. So this is a typical etching setup which I use in my lab. And what happens after the etching? So what happens during the etching is that the latent damage part is preferentially etched by the solution, whereas the other parts where the polymers were not broken is etched at a slower rate. So we have a cone-like structure made, which is easily visible using a microscope. So once you look at the surface of the CR39 after etching, we will see the particle tracks. And so in case if the CR39 is not exposed to any kind of radiation, what we will have is there will be no particle tracks from CR39. So figure G is SCR39, which is exposed to some particle source, and figure H is the one which is not exposed to the particle source. So we clearly see the difference. Another important point to note here is that since the condition for permanent track registration is 15 kiloelectron volt per micron, this is the threshold, it is important to note that beta particles, gamma rays, and thermal neutrons are not going to create tracks in CR39. just for the simple reason that it does not crosses the threshold, this threshold condition, the linear energy transfer threshold condition. So basically, CR39 is insensitive to thermal neutrons, beta rays, and gamma radiations. So how do we use CR39 for detecting thermal neutrons then? So we simply use the known knowledge that a boron-10 absorbs thermal neutrons and generate lithium and alpha particles. And these lithium and alpha particles have enough energy to generate permanent latent tracks in CR39. So how do we do that? In figure 1, I show a bare CR39. A is a bare CR39. This is not going to respond to thermal neutrons. And so what we do next is that we coat it with boron powder so that it becomes sensitive to thermal neutrons. And then to know what happens if there is no boron coating, I keep a bare CR39 along with it, which is not coated with boric acid. Okay, so boric acid is my source of boron here. And then one can cover it with some kind of plastic shielding if you want to put it inside a liquid solution or depending on your experimental needs. So here I have covered this CR39 boron coating with a total of 65 micron thick plastic shielding. So we'll call this boric acid coated CR39 as a BCR and the uncoated ones as a CCR. So CCR basically works as a control chip here. It is going to show us what happens if boric acid coating is not present. And so what happens after we use this detectors in any kind of exposure? We just simply do the imaging, and the imaging process is shown in figure 2. So this is the 4x6 mm chip, which could be a BCR or a CCR. So after exposure and etching, we just divide it into 4 parts and we image the 4 different parts, the left top, right bottom and left bottom of the surface of CR39. And then we count the number of tracks on this piece. So let's do some experiments with this BCR and CCR setup. So first what we are doing is we are exposing this BCR CCR to fast and slow neutron source. So what you see here is a thermal neutron source, and this thermal neutron source basically employs a plutonium beryllium source, a fast neutron source, which is thermalized using wax as a moderator. And so this yellow one is basically a plutonium beryllium source, and this all is this PUV source container. This is the wax drum, and this green colored is where we put our samples. So you can see this part here I have zoomed in just to explain what happens. So we have placed BCR and CCR side by side with the boron coating facing towards the neutron source. So the neutron source are basically going to react with this boron and generate lithium and alpha particles, which are going to be imprinted on this CR39 of this BCR. And this CCR, once again I would like to remind you, CCR is just a control chip. We do not have any kind of boron coating here. So we do this experiment for different time, and let's have a look at the results. So this is a plot of mean track counts which are observed on both BCR and CCR at different times. So this black data points represents the BCR counts, the mean BCR counts. Okay, so these are the mean BCR counts obtained on the chips for different times, and the red one is the mean BCR counts on the CCR. Once we deduct BCR minus CCR, we have this blue data points, and you can see that almost follows a linear relationship. So what do we get from this result? What we get is the data of thermal neutron detection efficiency of a BCR. How do we do that? We have already deducted BCR minus CCR. We know that the CCR is not going to respond to thermal neutrons, and it is going to respond to fast neutrons and charged particles which are present in any environment. And similarly, this BCR is also going to respond to the charged particles and the fast neutron, but on top of that, it is also going to respond to thermal neutrons. So once I deduct the signal of BCR minus CCR, what I expect is to have only the signals of thermal neutrons. Just to repeat, this black line represents the thermal neutron signals plus the fast neutron signals plus the charged particle which are present in the environment, and the red one includes the charged particles and the fast neutron signals. it is not going to detect thermal electron signal, because the thermal electron energy of the thermal electron is in milli-electron volt, and it is not going to create tracks on CR39. We have already discussed the condition for creation of tracks. So the blue line is expected to be representative of the thermal electron fluences in our experiments. So in this case, it is the thermal electron source that we have used. Just to an important point to note that any kind of thermal electron source is designed to convert the maximum fraction of population of the fast neutron being emitted to thermal neutron, but it's very hard to convert all of them to thermalize all of the fast neutrons is very hard actually. So there is some fraction of population which are going to be emerging as a fast neutrons and generating tracks on both BCR and CCR. So we know the thermal electron flux of that source that we have used, and using that data, we find out the detection efficiency of the BCR. So the BCR detection efficiency is found to be 1.6 into 10 to the power minus 3. So the order is important here, and this is the reference. All the references are in my last slide. You can one can have a look at that if you want to know the details of the thermal electron source. It's already published. Okay, now let's make a more generalized radiation field. So earlier we had slow neutron and fast neutron, and now we are going to mix alpha particle radiation. So for generating alpha particle radiation, I use these foliated welding rods, and so I arrange 8 of these rods next to each other and place BCR and CCR over it, so that alpha particle can cross this plastic sheet, which and then generate tracks on CR39. So again, it's going to create tracks on both BCR and CCR. We just have to make sure that the plastic coating that we are using on this BCR and CCR should not be thick enough so that it attenuates these alpha particles. So here I am just using 10 micron thick plastic sheets, just to make sure that the alpha particle crosses it and generates track on both BCR and CCR. So let's see the most generalized situation. We have a thermal neutron source which has some kind of fast neutron leakage. And then this red one is our alpha source that we have discussed in the last slide. These are the 2% foliated welding rod that I just showed in the previous slide. And then this green one is again our BCR and CCR. But what we have done here is we have flipped the boron coating side this time. The boron coating is facing is not facing the thermal neutron source. The thermal neutron source is anyways going to enter this BCR and generate and react with this boron coating and generate lithium and alpha particles, which are going to be imprinted on this BCR. And from top of this, alpha particles are also going to create particle tracks on this BCR and on this CCR. And the fast neutron, of course, are going to affect both BCR and CCR. And so this is the most general field. So that's why the title of this slide is Fast and Slow Neutron and Alpha Particles, Exposure to Fast, Slow and Alpha Particles. So let's have a look at the results. What happens if I do the experiment for 30 minutes? So in the case of alpha only irradiation, I find an average of a mean counts of 82 on BCR, 84 on CCR, and the difference is negligible. And if I expose this BCR and CCR to neutron source only, so by this N, I mean this thermal neutron source, which has a fast neutron leakage with it, component with it. So we have 253 counts on BCR and we have 100 counts on CCR. The difference is 153, which should correspond to the slow neutron fluences. And now the most general case, we have a neutron source and alpha source. We have 332 counts on BCR, and then we have 182 counts on CCR. The difference again is 150 plus minus 5.8. Please note that these errors are all the mean standard error of mean, because I have just taken an average over the counts on the BCRs and CCR. So these are not standard deviation but standard error of means. So you can see that in both the cases, we see that the results of the differences of BCR and CCR are quite similar within the error bars. So this tells us that our BCR-CCR methodology is working fine. So what do we learn from these experiments?
Excuse me, Dr. Kumar, you have 5 minutes to wrap up your conference, okay?
Okay. So we know that this BCR-CCR has been successful in providing intrinsic background, in removing the background radiations of fast neutron and charged particle, and has given us the true signal of the slow neutrons. And so it is a reliable detector in the mixed radiation field, and this can be utilized in plasma discharges, ANR type experiments where background signals can mimic neutron events. So now let's utilize this in our electrolysis experiments. So this is our electrolytic cell. This is how it looks. We have affixed BCR and CCRs here, and these are two magnets that we are using. We are just copying the methodology from Pam Bosch's experiments, and so here we are doing co-dimension experiments. And so the typical panels that we use to run these experiments from microamperes to a few milliamperes. And let's have a look at the results. So BCR, CCR are not quite visible here because of the electrolyte, but you can see here we have not filled the electrolyte and it's quite visible here. And these are the schematics. So let's have a look at the results. What happens in the D2 electrolysis placed under 0.25 Tesla field? So figure the top panel A, B, C, D represent the images on the BCR, on the four parts of the BCR. We see a number of tracks. So this is the left top part, 384 tracks, right top part 403 tracks, right bottom part 455 tracks, left bottom part of BCR 441 tracks. And the lower panel, figure E, F, G, H, shows us what CCR has recorded. This is very less as compared to the BCR. So let's have just go to the relevant information. After detecting the BCR background and the baseline of the CR39 sample, we get 413 tracks per 4.8 mm square as the representative BCR signal, and the CCR signal is 5.7. So clearly, we can deduct this 5.7 from this 413 and get an estimate of slow neutron signals. So this 5.7 could be anything. It could be charged particle, it could be a fast neutron also. But one thing we know for sure that it's not going to be a slow neutron signal because we don't have bone coating on this. Again, what happens if we remove the magnetic field? We get a reduction in the tracks on BCR. The average is 72 tracks, and CCR again gives very low tracks. So 72 as compared to 4, very significant numbers. I mean, very significant difference, 72 minus 4. What happens if we do the same experiments in light water? It is been done in presence of external field. This is should be presence of magnetic field. We have almost same kind of tracks which are being recorded on BCR and CCR. So here doing a difference of BCR and CCR is insignificant because the signals are almost same. So what we can conclude from these experiments is that the slow neutron flux, what we have observed in the heavy water electrolysis in presence of 0.25 Tesla, gives us a value of 8 neutrons per centimeter square per second. If I convert it to the neutron flux using the detection efficiency that we found of the BCR from our earlier experiments, it's 8 neutrons per centimeter square per second. This is averaged over the duration of the experimental time. And if we try to find out the activity of this source, it would be equivalent to a 6.8 nanocurie. This is just for normalization purposes. Usually nanocurie is used for a radioactive source. I am assuming that my cathode is being radioactive, a wire, and so it would be 6.8 nanocurie. And we also know that the absence of 0.25 Tesla external field has reduced the flux by the factor of 6. Okay, and the light water experiments in presence of 0.25 Tesla field gave negligible signal of thermal neutrons. So the last slide, summary and way forward. We have seen that the differential method of using CR39, which is BCR minus CCR, has enabled more faithful thermal neutron measurements in systems with unknown radiation fields. What I mean by that is that any kind of novel experiments where we do not know what kind of field it can generate, we should use BCR minus CCR, and not because there are many experiments that I have read where people only have used BCR, they have not done BCR minus CCR. So one has to make sure that they do the differential measurements to rule out the presence of fast neutrons and charged particle signals, which can mimic as a slow neutron signal on this BCR. This is very important. And then neutron loading is important for thermal neutron observation. This we have seen. And a magnetic field can be used to enhance such emission. This also we have seen. And the present observation aligns with the previous findings by Pamela Bosch, where they have demonstrated magnetic field enhanced charged particle emissions. So here we have just shown slow neutron emission enhancement in slow neutron emissions. And so the last point, in the future investigations, we are trying to involve a gadolinium. We are trying to mix gadolinium into the electrolyte, trying to leverage its high neutral capture cross-section to generate characteristic gamma emissions. And we are trying to detect these characteristic gamma rays using our high-purity germanium detectors. So thank you for your kind attentions. So these are some acknowledgements. Sandeep sir, Mrs. Ruer, Tushar Verma, Professor Pankaj Jain, and Professor Pala. Any comments can be addressed to these mail addresses.
Okay.
Questions, please.
Thank you very much again. I really appreciate your talk. And the session is open for questions. If you have any questions. Oh. I have one question then.
Sure.
Is there any way you could do calorimetry along with neutron detection?
Yes, we could have done it, but we couldn't find a suitable candidate because I do not have an expertise in calorimetry and I am nearly completing my thesis. But surely we'll have some new students who are going to do it.
Okay. Well, I like calorimetry. I mean, I don't. It's not that I like it, but I've done it. So next time I come to India, I will visit you then. Okay. Thank you.
Sure.
Thank you so much again for your contribution, Mr. Kumar.
Thank you for providing me this opportunity.
Very good work. Bye-bye.